over 4 pi epsilon naught over capital R squared. Now, once you go over capital R, now once little r is larger than capital R, this formula now applies. This one applies. So let's see what this one says. Let's start with little r equal to capital R. What do we get if we plug in little r equal to capital R? What do we get? You will get 1 over 4 pi epsilon naught q over capital R squared. You will get exactly this one. So, and then it drops as 1 over r squared, right? Now as you go, you're divided by 1 over r squared, so it becomes less and less as capital R. As little r grows, it goes like. Okay, so that's inside and outside of a sphere. Solidly charged. Okay. Okay. In the homework, I gave you a question similar to it in homework. This next homework, the one you have, is it 7 or 8? I forgot.
7.
Probably 7, right? Yeah, homework 7. In the book, they have a charge that depends on R, charge density that depends on R. And you're asked to find how much Q is inside, you have to integrate. So you should start homework 7 kind of early. You should start it like right after the quiz that you have today. Okay. Yeah. So the rest of this week, and we're going to spend it on Gauss's law. Okay. So now the next thing is a line of charge. Let's see if we can do it in the next, let's say, 9 or 10 minutes. Let's do a line of charge. I think we know the result already. What's the, by the way, can I erase here? Yeah? No objections? Okay. So for an infinite line of charge, we know the answer. We did it by direct integration. Charge. And it's uniformly charged, and the charge density is lambda. So here's the line of charge. Right? This is plus, right? So in what let's say I'm a distance r away. I'm here, a distance r away. In what direction would the field be? Would it be this way, or this way?
That way.
This way. Straight up. So if the line is coming towards you, it's coming towards you. If this is the line and it's coming towards you, the field looks like this, right? The line, let's say here is a line of charge. It's coming towards you. The field points like this. Like spikes like that. Okay? Does that make sense? Like the, you call it those in your bicycle wheel. Yeah, looks like that. So the electric field has to point this way. So now that's your line of charge. Let's say here's your line of charge. Except that this one is not infinite, it's very small. I wish I had the longer one. So what kind of symmetry is there? Cylindrical, yeah. Think like if you're going to mail this thing, send it as a package, how would you package it in the most efficient way? You probably wouldn't use a spherical package, right? That's kind of a waste this way. So you would use probably a cylindrical package, like something like this, right? Like a cube. So the symmetry here is cylindrical symmetry. So we're going to use Gauss's law using a cylindrical Gaussian surface. And here's how it looks like. I know, as long as I'm on this, imagine my line of charge is here, right? That's at the center of this cylinder. Anywhere on the surface of this cylinder, the electric field will point perpendicular or parallel to the area, and it also has constant value as long as I'm the same distance away from the line of charge. Okay? Does that make sense? Imagine there is a line of charge coming out like a wire, like this, and this is wrapping it. So my Gaussian surface will look like this. It's a cylinder of radius r, and let's say it has a length L, and radius r. So the cylinder, though, Gauss's law says the electric says this. It says the electric flux E dot dA equals to Q enclosed over epsilon naught, but it has to be a closed surface. So is this cylinder here, the one I have with me, is it a closed surface? No, it's open, right? I can see it. So I need a cap here and a cap here. So the cylinder will have the like the end sides here, the sides of the cylinder, and then the curvy side, right? The one that's curved. So E dot dA is equal to Q over epsilon naught. So I'm going to I'm integrating over the closed cylinder, right? For a sphere, I mean, it was just one piece. But for a cylinder, you have the side, and then you have the two caps at the end. So you would have this closed integral. So it will have the curved part of the cylinder. We have to do E dot dA. I'm going to break this integral into three integrals. One around the curved part, and then the one from the caps. Cap 1 and cap 2. The top cap and the bottom cap. Plus the integral over cap 1, let's say, and then have E dot dA. And you will see it looks complicated, but it's actually not. Plus E dot dA from the second cap equals to Q enclosed over epsilon naught. Now, how much charge will be enclosed in my cylinder? Right? How much charge will be enclosed? Well, I will enclose this much of the wire, right? The wire is infinitely long, but I'm only enclosing this part of the wire. So how much charge will be enclosed? What does lambda represent? Charge per unit of what? Length.
Yeah.
So if I multiply the charge density lambda by length, that will give me the charge enclosed within my surface. So within my surface, the charge enclosed is just lambda times the length of this surface here, the length this way, over epsilon naught. Now let's, this is cap 1, and then the other cap 2. Let's deal with the caps because they're easier. Electric field again. So here's the cylinder. In what direction is the field? Well, the field is perpendicular, is this way, right? Everywhere, it's this way. In what direction is this cap pointing?
Perpendicular.
Towards you, right? Yeah, that way. So what's E dot dA there?
0.
0. So over this first cap it's 0. Well, same thing here. This cap is pointing towards you, so that E dot dA will be 0. So 0, 0. So this just contribute nothing. Now how about this one? Well, let's see. So this went to 0. So on the right hand side I have lambda L over epsilon naught. What's E dot dA here? Now, E points this way. In what direction is dA from the side? From the curved side. In what direction does dA point?
Away from the surface.
Away. So it's parallel to E. So it's parallel to E. So E dot dA becomes just E times dA from the curved part. So it just becomes E times dA. Okay? But E, as long as I'm on the surface of that cylinder, is E having different values or the same value?
Constant.
Constant. So see, that's why you want the perpendicular part. That goes to 0. And then the curved part became the parallel. And so E goes here, EA. lambda L over epsilon naught. And so now dA, what's dA? Well, it's the area of this curved part. It's 2 pi r by L. So the area, what's the area of this curved part?
Oh god.
2 pi r times L.
Ah.
Yeah. So 2 pi r is the circumference
Oh yeah.
times L.
True.
That would be the, yeah. I mean, imagine like I cut this cylinder and I open it. Here it is. If I have my cylinder, right? This is 2 pi r, and this is L. If I open it, so this is 2 pi r times L. That's the area. So 2 pi r times L. So this becomes just 2 pi r times L, lambda L over epsilon naught. And notice the L and the L cancels. And you get, oh, there is the E, right? E. Forget E. So you get E will equal to lambda over 2 pi epsilon naught times R. You remember we got this last chapter, integration. Yeah.
So basically, it doesn't matter if you have caps on your cylinder or not.
Well, Gauss's law requires that you have a closed surface.
All right.
Yeah, the caps contributed nothing to the flux, but you have to have a closed surface.
Okay.
I think it's reasonable to probably just, yeah, I'm going to start the quiz in about 4 minutes or so. Let's do this. If you want to use the restroom, come back, and I will see you in about 4 minutes.